So hello students, I'm solving this NET June 2013 paper. Okay, so this question is asked from solid physics. Topic was lattice vibration. So they have given one dispersion relation, and they're asking what is the velocity of sound wave. Okay, so they are asked velocity of sound waves. Okay, so as you can see, this is the dispersion relation for a one-dimensional diatomic chain of atoms. Okay, diatomic lattice. Okay, so now we know the dispersion relation for a diatomic lattice. Okay, has acoustic as well as optical branch. Okay, so if we plot the graph, okay, for dispersion relation omega versus k, so we can see this graph has two branches. Okay, so one is acoustic branch. Okay, this is acoustic branch. Okay, and other one is optical branch. Okay, so this is omega. Okay, this is k, and this is the first William John. So from minus pi by a to plus pi by a. Okay, and in this question they're asking what is the velocity of sound waves. Okay, so we know that velocity of sound wave we can calculate from the acoustic branch. Okay, in acoustic branch, okay, for long wavelength region, okay, long wavelength region means when k is almost equal to 0, k tends to 0. Okay, this omega k curves are linear. Okay, so the slope of this curve, okay, the slope of this curve will give you the velocity of sound. Okay, so let us calculate the dispersion relation for long wavelength, that is when k tends to 0 condition. Okay, so we can write when k tends to 0, okay, that is long wavelength region. When k tends to 0, that is long wavelength region. Okay, I can write sine qa, sine qa. Okay, here they have mentioned wave vector by q. Okay, so we can write q tends to 0, so sine qa, okay, will be almost equal to qa. Okay, so this is sine square q by qa by 2, qa by 2. Okay, now let us solve this problem, okay, by putting these values in this expression. So this will give you omega square q k 1 upon m1 plus 1 upon m2. Okay, so 1 plus minus, so we have to take acoustic branch. Okay, that means lower branch, so we'll take it here minus. So this will give me 1 minus 4 m1 m2 upon m1 plus m2 ka square, and this will become q square a square by 2. Okay, and now 4. Okay, so now we can solve it further. So if you solve this one, this will give me this 4 cancel. Okay, and this is k 1 upon m1 plus 1 upon m2. Okay, 1 minus. Okay, so this we can open by binomial. Okay, we know 1 minus x. Okay, so qa is a lattice constant, q is also very small, so this whole quantity is less than 1. Okay, because a is a lattice constant, okay, whose value is in angstrom. So I can write 1 minus x. Okay, that is 1 minus x power half is equal to 1 minus half x. Okay, so 1 minus half x. Okay, so let me solve this by this under root. Okay, this will give me, if we expand this one, this will give me 1 minus half x. Okay, so this will become 4. This will become m1 m2. Okay, m1 plus m2 whole square q square a square. Okay, and now this one cancel. Okay, and we will get this k. Okay, k equals to 1 upon m1 plus 1 upon m2, okay, into 1 upon m1 plus m2, okay, q square a square upon m1 plus m2 square, okay. So if we solve it further, this will give you, okay, omega square q will give you k, okay, m1 plus m2, okay, upon m1 m2, okay, and this will become 2 half m1 m2 q square a square, okay, m1 plus m2 ka whole square. So this power will cancel, okay, this m1 m2 cancel, okay. So we'll be left with only omega square q as k by 2, okay, k by 2, okay, and q square a square upon m1 plus m2, okay. Now we want the sound velocity, okay. So what will be sound velocity? Let us take it under root of this one, okay. This will give you omega q. Omega q is equal to under root, okay, k by 2 1 upon m1 plus m2, okay, and this become qa, okay. Now sound velocity is equal to d omega upon dq, okay. This will give you under root k a square 2 m1 plus m2, okay, and this was given as the option b, okay. So option b is the your correct answer for this question, okay. Thank you very much.